Hello, period 4, and anybody else from Algebra 2 who is watching this video lesson of what we were learning on day 2 of week 2. This is using the angle of rotation and the reference angle to do sine ratios in our unit circle. So if you would kindly please hit pause and do these 3 problems to warm up to get ready for the rest of the lesson. When you're ready, first thing you always do is to pay attention to 2 different things. One is the quadrant, where your terminal ray rotates to, and also whether or not that terminal ray, well, actually what angles it appears between. So I'm always starting at this pink part of the positive x-axis, where it's 0 degrees, 90 degrees when I rotate a quarter, 180 degrees when I go halfway around, 270 degrees, and if I go back to the beginning, it's 360 degrees. My angle happens to be in quadrant 2. It says it's an angle of rotation of 100, so starting from that initial ray to the terminal ray is 100 degrees. To find the reference angle, since you didn't make it all the way to 180 degrees, it's going to be 180 minus 100, and that's going to give you 80 degrees. Now, to find another angle with the same height, there are 2 ways to do it. Number 1, you can use what you know about symmetry and say, go backwards to the same height on the circle. If this reference angle is 80 degrees, then this reference angle is 80 degrees. And you can say 80 degrees has the same sine ratio or the same height in the circle as 100 degrees of the angle of rotation. You could also take the angle of rotation and you could add 360 degrees, because then you would be making a full rotation. So to 100 degrees, and then a whole nother rotation makes it another 360 degrees, 460 degrees for our first warm-up. Our second warm-up takes place in the 3rd quadrant. This is 180 degrees. If I've rotated to 240, our reference angle will be 240 minus 180, which is 60 degrees. You can rotate here, and that would be the same sine or the same height, or you can take your 240 degrees and add 360. Do not add 360 to the reference angle. Add it to the angle of rotation. 600 degrees even. In the first quadrant, the angle of rotation is the same as the reference angle because it's positive and between 0 and 90. And to get an angle with the same height, you could either use this is the reference angle, and then say 180 minus 72, I believe that's 108, 108, oh, that's not 108, 108 would be the same sine value as 72. Last one is 304. You can see that it takes place in quadrant 4, between 270 degrees and 360 degrees. When you are in quadrant 4, to find the reference angle, it's going to be 360, so as if you rotated all the way around, and then you're going to subtract the angle of rotation, 304. So that reference angle will be 56 degrees. And again, to find the same height, you could do 304 plus 360 for 664 degrees. Or you can rotate to the third and say this and this, and then you would just have to measure this here. So that's our warm-up. Today for our homework at the end of week 2 is homework number 5. Homework number 5 is due by Monday or Sunday at midnight. Just a review of what we just did in the warm-up in terms of how you calculate what the reference angle is depending on what quadrant you're in. So again, I'm going to label this 0 degrees, 90 degrees, 180 degrees, 270 degrees, and then the quadrants are already labeled. The reference triangle, so we have a reference angle inside the reference triangle, is formed by dropping a perpendicular from the terminal ray of a standard position angle. Remember, standard position just means that you start here at 0 degrees and start rotating counterclockwise to the x-axis. That's the other thing that's important. The reference of either the reference triangle or the reference angle is always in reference to the x-axis. So when they're talking about dropping a line, or basically going up from the terminal side to the x-axis, it's always to the x-axis. The reference is to the x-axis. Now, you can see here that they're calling the reference angle theta prime. Okay, when you have a little mark like that, that's called theta prime. A lot of times, I'm going to label my reference angle with the little r. That might be easier to remember. And remember, as I taught you before, it's always a positive acute angle. When you are finding the reference angle and the angle of rotation in quadrant 1, the reference angle and the angle of rotation are the same. Any angle between 0 and 90 degrees is going to be an acute positive angle, so they're the same. There's no addition or subtraction in quadrant 1. In quadrant 2, you're going to take your angle of rotation and you are going to subtract that from 180 to get the reference angle. Or you can take 180 and subtract the reference angle, and that will get you the angle of rotation. But either way, it's going to be 180 minus the angle of rotation or the reference angle. To find the angle of rotation in quadrant 3, it's going to be 180 plus the reference angle. Or you can do the angle of rotation minus 180, and that will give you the reference angle. Basically, it's always some kind of addition or subtraction to get the reference angle. Lastly, in quadrant 4, if you went all the way around, it would be 360 degrees. But if you do 360 degrees and subtract the reference angle, you will get the angle of rotation in quadrant 4. It's a good thing to memorize this page. This is just a reminder of how we have used Pythagorean in our calculations of our right triangles, and I'm just going to use number 28 to do my example. So I can see that across from the 90-degree angle is 7. So if I'm setting up Pythagorean, c squared is always going to be my hypotenuse squared. The other side they give me is 6 squared. So 6 squared plus the other side squared equals the hypotenuse squared. That means b squared is 49 minus 36. B squared is, looks like 13. So b equals square root of 13. So x equals our missing side, square root of 13. Now, what does that have to do? What does Pythagorean theorem have to do with the standard equation of a circle whose center, the center of the circle, is at the origin? Look at the standard form of the equation of your circle. It's x squared plus y squared equals r squared. Look how similar that is to a squared plus b squared equals c squared. And remember that I told you the radius equals the hypotenuse. So I'm already making connections between the circle and the right triangle. When I'm creating my triangle in the circle, when I move from the center to the bottom of my right triangle, that is an x distance. When I go up from the right angle to the circumference of the circle, that's a y difference. Now, you can say this is hypotenuse, this is opposite, because remember my reference angle is going to be here. And you can say this is adjacent, but again, that's the same thing. Opposite squared plus adjacent squared equals hypotenuse squared. They're all the same. Circle, right triangle, and Pythagorean theorem. That's going to be very important to figure out the problems on the next page. So in this diagram, angle theta is between 0 and 90. So I'm already in quadrant 1. The right triangle has been drawn. So basically, the terminal ray rotated from the positive side of the x-axis to this point on the circle. As we told you before, you're going to drop a line. When you drop a line, your right triangle is formed. A right triangle has been drawn in quadrant 1, just like we drew triangles on our Ferris wheel tasks. Based on this diagram, the right triangle definition of sine now uses x, y, and r. Our r is the same as our hypotenuse. Our opposite is the same as the x value. The opposite is the same as our y value. And x is the same as our adjacent value. So I can do sine theta as opposite over hypotenuse. That comes from so in SOHCAHTOA. And now, since opposite is y and hypotenuse is the same as radius, I can say that sine theta is the same as y over r. We can do the same thing with cosine. Cosine theta is our ca in SOHCAHTOA, which means adjacent over hypotenuse. But now, since I'm switching the definition to the unit circle, adjacent is not described as adjacent anymore. Adjacent is described as x. Hypotenuse is the same as the radius. So now when I talk about cosine, I will often be using x over r. We'll use this definition for any angle of rotation. So what that's trying to say is, our example is in quadrant 1. If it's any angle of rotation, we can be in any of the quadrants in our circle. So first example, please pay attention. This is similar to your homework. So if you can do this and follow this, you'll be able to do your homework. Step 1, even before it asks A to find the radius, you're going to graph this point on your circle. -3 says go over 3 to the left and up to 4. And this is going to be a point on our circle. What circle? Our circle where the equation is x squared plus y squared equals 25. Now, what is the radius of this circle? There are 2 different ways you can do this. You can say Pythagorean says, well, first of all, let me draw things because I need my initial ray. I need it rotating until I'm still from the center, but now I'm going through this point. So drop a line. That's how we make the triangle. So here is the triangle I'm making. This is the point where I drop down from. This distance is -3, and this distance is 4. Now, I know a triangle cannot have a side of -3, but we're not talking about really a real triangle. We're talking about using the methods of a right triangle in order to solve circle problems. So if I am to the left of the y-axis, that's where x is negative. So now I can use Pythagorean. Okay, this is a right angle here. What's missing is the radius. One side of the circle is -3. So -3 squared. The other side, I'm sorry, of the triangle. The other side of the triangle is 4. 4 squared equals r squared. 9 plus 16 equals r squared. 25 equals r squared. R equals 5. There's another easier way to do this. Remember, work efficiently and effectively. If the equation of our circle is x squared plus y squared equals r squared, you don't even need to square -3 and 4. You can say, oh, r squared equals 25. So that means r equals 5. Our radius equals 5. The next step is not calculating anything. It says draw the circle. Once you have the radius, put the radius on each of the axes. So a radius of 5 says go up to 5. That's one radius. All radii are the same measurement on the circle. Go over to +5 on the x-axis. Go down to -5 on the y-axis. Go down to, across to the left to -5 on the x-axis. And now here is the circle that's formed. Look at my circle. It goes through the radius like it's supposed to, because the radius is between the center and the circumference, and it goes through our point on the circle. We have our initial ray, where we started on the positive side of the x-axis, and we have our terminal ray, where we stopped in quadrant 2. Next question, for the angle of rotation you just drew, what would be the value of the sine? Now, the value of our sine for this angle. So again, I'm going to say this angle here between the initial ray and the terminal ray. I'm sorry, that's not the reference angle. I wrote the wrong thing. Hold on. That's your angle of rotation. That's your angle of rotation. This is your reference angle right here. Theta little r. And that theta little r is going to be your definition of sine. Both the angle of rotation and the reference angle have the same sine value. Remember how we said they were at the same height on the circle? That means they have the same y value. If they have the same y value, and I drew a triangle here, this would be the same triangle, just rotated around the origin. So if it's the same triangle, it has the same sine value if I just use the reference angle. So I'm going to say sine of our angle, and I'm going to use the reference angle, is our y value over our r value. I'm going to go over to my triangle in quadrant 2, and I'm going to say, what is the sine ratio? Well, across from the reference angle is 4. Our radius calculated in part A is 5. So our sine value or our sine ratio is 4/5. Now, D asks, what is the measure of the angle of rotation? How do you determine the size of the angle of rotation? Well, I already know that sine of the reference angle is 4/5. And I taught you using inverses that to find an angle when I'm given a ratio is going to be inverse sine. In your calculator, you're going to hit the second button and then you're going to hit sine. And then in the parentheses, you're going to put 4/5, and your calculator is going to spit out a angle measurement. So let me see if I can call up my calculator. It looks like it's going to take a minute to load. And in the meantime, we can see the note on the bottom. It says the calculator will sometimes give you the reference angle. You need to use your knowledge of quadrants to find the angle of rotation. So depending on what angle your calculator spits out, you may need to change what the answer is depending on what quadrant you're in. So let me see if I can go to my calculator now. Inverse sine is second sine. Nope, I don't know why that didn't work. Second sine 4 divided by 5. That answer gives me the measurement of the reference angle. It's the acute angle in the triangle, because it can't be the angle of rotation. The angle of rotation takes you to quadrant 2. This is in quadrant 1, 53 degrees. So that tells you that this is our angle of, our reference angle. So I'm just going to round it to the nearest degree and say 53 degrees. And remember, once I know how much the angle, the reference angle is, if this is 180 degrees, then the angle of rotation, which is just plain old theta, equals 180 minus 53. We talked about that on the previous page. That is going to be 127 degrees. So I hope this lesson helped. I'm going to publish it in the module. Come to class with questions on Monday and Tuesday. And you guys have a great weekend.